Hello, everyone. Welcome to our webinar. Before I start talking about the technical stuff, I want to quickly introduce myself. I am a Cisco certified associate professional and expert with over 12 years of experience. My background is a mix of production systems activities and training. I worked for one of the biggest Cisco training companies for several years. I ran my own training business. Of course, I was also working for several companies where I was responsible for production networks, like maintenance, like troubleshooting, like design. My focus is generally on network security, but I also have a pretty decent experience with routing and switching technologies. And maybe just to quickly show you some of the courses we added recently. I currently work as a full-time instructor with INE. Just to show you some of the content that we added recently. Most of the stuff focuses on network security and is related to the expert level certification. So this is going to be CCIE level courses. But we also have some CCNA stuff like routing technologies for beginners, maybe layer 2 technologies for beginners. So pretty much anything that you see with beginners included in the title, this is for CCNA. Then professionals, this is talking about the CCNP. And then some of the other courses, it is going to be CCNA, at this time for security, and then also CCIE staff, CCIE security version 5. I would say this is going to be this, secure connectivity, perimeter security. This is just a couple of the most recently added courses. There are more. Some of them focus on individual technologies. Some others are related to the certification. Okay, what we will take a look at today is FlexVPNs. Now, I want to quickly discuss the technology from a high-level perspective. I want to tell you about the differences between FlexVPNs and some other Cisco iOS ID1 based solutions that we used to deal with previously before introduction of ID2. And we will take a look at the main building blocks of FlexVPNs. I'm gonna I'll tell you about the components, about the framework, configuration framework itself, and we will of course have a demonstration. It is going to be a pretty simple config where I'm going to show you how to deploy a site-to-site tunnel between two iOS devices. It is going to be router 1 and router 2. Those devices will act as VPN peers. So what I'm trying to emulate here is more of like two separate, I would say, branch offices, or maybe central location and branch office that we want to connect. And the connectivity is going to be provided over the internet. So we assume that we don't manage those networks in between R1 and R2. So R1 and R2, just to recap, this is going to make the VPN peers in our session. But before we get to the actual configuration, to the demonstration, I want to quickly take a look at the technology, as I said, from a high-level perspective. So what is FlexVPN? This is a pretty recent solution, Cisco iOS solution for deploying VPN technologies, different types of VPN technologies, that is supposed to provide us a single configuration framework, like a single CLI for different types of VPN technologies. Now, if you think about ID1, let's say the DMVPN, and let's say EasyVPN. This actually applies to pretty much every single ID1 based solution, but it's going to be pretty easy to show you the differences when looking at DMVPNs and EasyVPNs in particular. Now, if you think about the configuration syntax, configuration framework, it is definitely not the same. So if you plan to go for DMVPNs, in most cases you will be dealing with MGRE tunnel, at least one multi-point GRE tunnel interface. With EasyVPNs, it is going to be a tunnel like a static or dynamic tunnel, or maybe it is going to be a crypto map. This, of course, affects the entire configuration. Plus, there is going to be some features that you will see in one solution, but not in the other. Like in case of DMVPNs, this is going to be NHRP. With EasyVPNs, it is going to be, let's say, AAA integration for authentication and authorization. If you go over those other IPv1 based solutions, implementations, you will spot some additional differences, but the configuration and support, or just lack of support for certain features, these two are probably the most important ones. So not so longer with FlexVPNs, because with FlexVPNs, we're going to be dealing with three main components that will be kind of like shared by any of the VPN topologies and any of the VPN solutions you may want to deploy. There is going to be this protocol that we use for negotiation, and it is always going to be IKE version 2, not IKE v1. It's actually the moment when IETF came up with IKE v2. Cisco decided that it's a pretty good moment to come up with a new configuration framework. So instead of trying to introduce IKE v2 to the existing configuration syntax building blocks used with IKE v1, where as we now know they are different, they came up with a single solution, one CLI, that will allow us to deploy those different types of IKE v2 based VPNs. There is going to be the tunnel interface, which in case of FlexVPNs is always going to be point-to-point. So this is no longer optional like with IKE v1. We could use a crypto map, we could build a static or dynamic VTY, maybe use MGRE. Not with FlexVPNs. FlexVPNs, they will always rely on tunnel interfaces. This is not optional. But what is optional is integration with AAA. Now, AAA integration is optional in certain deployments, in certain VPN topologies. Like you don't need to use this component, let's say for site-to-site VPNs, but if you plan to go for remote access or maybe spoke-to-spoke, you will have to integrate your FlexVPN with AAA. And I will actually show you today how to do this basic integration. We will take a look at authorization, which is a method of pulling the attributes from the session attributes from the database. In our case, it is going to be the local database. And those attributes will be then applied to the session to exchange some information, some additional information between the VPN peers. Okay, now talking about the negotiation, talking about the actual specifics related to what happens in the background when you use IKE v1 versus IKE v2, the high-level process is going to be actually very similar. So there are some optimizations that were made to IKE v2, like the amount of messages, the actual complexity of the exchange. But from a very high-level perspective, it's going to be pretty much the same process. You will see the so-called IKE SA init negotiation, which is used to come up with a single secure tunnel that will be then used to protect another negotiation. So the goal of this first exchange is going to be to come up with a set of keys. The devices will also negotiate cryptographic functions. And then all this together will allow us to build a single tunnel management connection. And this is going to be that ICSA. And this first tunnel is going to be then used to protect second negotiation that is known as INE authentication. Okay, now since we already have the keys and we know the cryptographic functions, this information, the second exchange is going to be already protected within this tunnel. And now the goal of the second negotiation is going to be to come up with two other security associations, which is known as child assays in the ID2's nomenclature. One of those is going to be used to protect the incoming data, and then the other one is going to be used to protect the outgoing data. So what we send to the peer, and this is also protected, but this time with the keys negotiated by INE authentication exchange, during the INE authentication exchange. So we still have one main assay that manages subsequent negotiation, and this is needed so we can negotiate additional keys that will be then eventually used to protect the data packets and of course to authenticate our peers. Okay, now from the configuration standpoint, what we will have to think about as we deploy the tunnel, in my opinion, it's pretty easy it makes sense to kind of like break those components down into these two negotiations. Like, which of the elements do I need to create for ICSA init exchange versus what components are needed to finish the configuration related to the authentication negotiation. And the ICSA init this is going to be this exchange number one. What we will have to define here is going to be first and foremost a proposal. Okay, proposal, this is basically an equivalent of INE policy. I'm not going to put this here because I don't want to make this explanation confusing. There is still going to be a policy with INE2 with FlexVPNs, but the role of the INE2 policy of this component is going to be just to activate the proposal. So it's going to be the proposal, as we will see, what contains the security functions. So proposal and the policy, this is what we need to think about to cover this first exchange. Then for the second exchange, INE authentication, there are going to be several other things that we will have to deploy. And this is going to be first and foremost the credential store. So credential store is needed for, this is just a place where we will store our authentication data. And in general, authentication in INE2 can be performed using three different methods. We've got keys and certificates. So this is the same as with INE1. But in addition to that, we also have IP that is generally used for user authentication. There is also what is known as AnyConnect IP, where the difference between IP and AnyConnect IP is that IP requires radius, so it would be radius what makes the credential store in this case, or where with AnyConnect IP, it is going to be the FlexVPN server itself what stores the credentials. Now with keys and certificates, this is generally used for device authentication. So whenever you build a tunnel between, let's say, two iOS devices, or maybe iOS and the ASA, it is going to be, you will authenticate those devices using these two methods. You want to go for remote access VPNs, where the plan is going to be to perform authentication and authorization based on the group a user belongs to, or maybe you want to do this on a per user basis, you will have to use IP-based authentication. So credentials stored in our case, as we will see, this is going to be the iOS device itself. This is the simplest method. I'm going to store keys in the running configuration. But then another important component is going to be to specify, configure a profile, and it is going to be INE profile. We'll have to define here. This is actually the most important component of any FlexVPN deployment, because the profile acts as a repository of non-negotiable parameters for the session, which includes authentication method. Authentication in INE v2 is no longer negotiated. It is defined statically on our peers. What's even more important is that authentication method doesn't have to be the same. So it means that I can authenticate my peer. Actually, I can authenticate to the peer, let's say with keys, and peer can authenticate me with certificates. You can do something like this in INE v2. If you go for keys, a key-based authentication for both directions, you could even use different keys. It wasn't possible with INE v1, but we can do this in INE v2. The second role of the profile, the second main role of the profile, is to enforce our policy for the session. It's not going to be the session attributes what the profile stores, but I'm just going to say enforce policy. And this is going to be implemented by using a AAA and what is known as configuration exchange, where configuration exchange is going to act as a transport for those attributes. Okay, what else do we need to define to finish our INE authentication portion of the config? We've got the credential store, we've got the profile, but there is still going to be that IPsec portion, what we have to think about. So IPsec, this is all that is related to the data plane protection. This is what we will use to protect the data. And for IPsec, we will have to build, configure a transform set. We will have to configure a profile, but this time this is going to be a IPsec profile, not INE profile. So this here is something different than this profile. The role of the IPsec profile is going to be to point to the transform set or just activate the transform set. And it is also going to be used to activate our INE v2 profile to, in this case, select INE v2 as the protocol for the session. So at least these two components is what we will need to define in the IPsec profile. And then for IPsec, there is also going to be one more component. Don't forget about the tunnel interface configuration. So this is exactly what I want to show you today. We will also talk a little bit about control plane for FlexVPNs. We will take a look at 3 different methods as what we can use to enforce, just establish this end-to-end secure connectivity in the data plane. Okay, so just to make it clear once again, router 1 and router 2, this is what we will use in this session. Like if R1 belongs to branch, let's say office number 1, R2 belongs to a different office, we want to communicate these 2 offices together across the internet. And we're going to take this approach We're going to take a look at those configuration components one by one. And then towards the end of the session, I'm also going to discuss our free control plane options. And I will also show you a slightly more advanced configuration. We will discuss the configuration exchange and the different ways as how configuration exchange is actually achieved. Okay, I'm going to start our config. Maybe let me pull up the topology in the same time. We'll also take a look at documentation, but not at this point. I'm gonna put it down somewhere here so we see exactly what peer, what device I am on, and what are the different addresses that I will be referring to in this session. Okay, I'm gonna start our setup with a basic connectivity test. So the goal here is going to be to use gig00 of router 1 and gig00 of router 2. These two interfaces will be used to provide transport for our IPsec tunnel. So before I start building my configuration, I want to test connectivity between these two. I'm going to ping from router 1 from this gig00 1111. I'm going to try to reach 192.0.2.2. We see we have connectivity. We've got IP reachability, and we know that at least ICMP is opened, is allowed in the data plane between router 1 and router 2. Okay, this doesn't necessarily mean, it doesn't have to mean that we also have UDP port 500 reachability, which is what we will need for IPv2 negotiation. It could be also port 4500 if there was some sort of translation going on between R1 and R2 that would change the source address in those packets, source or destination address in those packets. Plus, we will also have to think about the connectivity in the data plane, because remember that the original packet, clear text packet, is going to look differently after applying IPsec services. Instead of seeing this regular or layer 4 header, such as UDP or TCP, we're going to see ESP or authentication header, depending on how we configured our policies. Okay, at this point, we will leave the UDP 500 and ESP connectivity. We will get back to this topic as we start testing our tunnels, but I can definitely tell you that there is going to be some problems in our case, given the fact that we have a firewall between the VPN peers. Okay, so let's start with the configuration. I'm going to build a proposal, which is where I'm going to specify our cryptographic functions for IKC init. I'm going to call it IKProf. And notice what it tells us here. It says that the proposal must either have a set of encryption algorithms other than AES Galois counter mode, then integrity and Diffie-Hellman, or if you go for this encryption, AES GCM, you're still supposed to specify PRF and Diffie-Hellman, but not integrity. And the reason that you don't have to specify integrity when you go for this encryption cipher is that AES GCM provides encryption and integrity checks on its own. And if you want to use this function and possibly specify some other encryption algorithms, you'll have to add them to separate proposals. We will go for a regular AES. I'm going to say that for encryption, you will want to use counter-based AES 128 bits. Then Diffie-Hellman group, let's choose 14. And then for integrity, I'm going to say SAJ 256. Do show crypto IB2 proposal. Notice that the pseudo random function PRF in our proposal, I didn't have to specify it because it is automatically set to match the integrity function. The pseudo random function, this is used during the authentication when you do the hash for authentication/integrity. And by default, iOS sets this algorithm. It uses the same one as what you put for integrity. Okay, this proposal is not active at this point. We have to put it under a policy. So we will go to the policy. I'm going to call it IPOL. And it says it must have at least one proposal attached. We not only have a lot of options here, we could potentially want to use this keyword match, which is just a method of tying a policy to either a local address, local interface. Like I said, address is only the local option, right? What I can use over here. Or we could use this policy and bind this policy to a certain VRF. If you don't specify anything, it is going to apply to all interfaces, all VRFs, which is going to work pretty fine here. I just have to tell it what's the proposal name. It's I called INE proposal like prof. That's fine. I'll call it like prof. Put it over here. Say do showdown section ID2. Okay, so the proposal and the policy activates the proposal. Nothing special here. Now for the second step, for the second negotiation, INE authentication, as I said, we will have to, first and foremost, we will have to think about the credential store. So I'm going to say crypto ID2 key ring. Since I'm going to use a key-based authentication, I'm going to store those keys locally on iOS in the running configuration. I have to build a key ring, and this is what I'm going to use to store those keys. Let's call it K ring like that. And I'm going to say that for my peer, I'm on R1, so my peer is going to be router 2. This is just to put a descriptive name for your peers, so we know which keys, what keys, or just what key belongs to what peer. And then from within the peer block, I can specify the actual address of the peer. In our case, this is going to be 192.0.2.2. This is R2. And I can specify the actual key. Now, I have an option to use local or remote keywords, but they would only come into play if I plan to use different keys for different direction of authentication, like what key I want to use to authenticate to the peer versus which of the keys I'm going to use to authenticate the peer. In our case, there's going to be a single key Cisco, and this key is going to be used to authenticate myself to the peer, and we will use the same key to authenticate the peer. So it's like a bidirectional key, same config style as what we used to see with ID1. Okay, I'm going to verify this configuration. 192.0.2.2, this looks good. This is for my peer. Moving on, we will now define a profile. Crypto ID2. Let's call it iProf like that. And it says that the minimum, our profile must be configured with a local and remote authentication method, because this is something that is no longer negotiated in ID2. Plus, we also need to specify at least one match statement. The match statement is used to catch the connection. Like if someone replies back to us, or maybe initiates a connection to us, the profile must know which connection it should apply to. So this is what we control with the match command. And the simplest method with key-based authentication is going to be to look for the address of the peer. It's going to be the match identity command with the remote option, remote address. I'm looking for 192.0.2.2. So this is identity of my peer. Okay, then for authentication, I'm gonna say that I will authenticate to the peer with keys. This is another place where you could also specify the key itself. We've got the key ring, so we don't need to use it. And I will also tell it that we will authenticate our peer with keys. This shall run section, let's say profile. I forgot to put one additional thing here to the profile. I have to tell it what credential store I use to keep my credentials. In our case, it is keyring with this name. It is a local keyring. Let's recap on this configuration. Proposal policy, and then keyring and profile. Another component is going to be to come up with a tunnel. Not tunnel. Tunnel is going to be the last component. We still need to define our IPsec transform set and then the profile. So this stuff is actually the same as with ID1. Crypto IPsec transform set, I'm going to call it set 1. Let's go for ESP triple DS, and let's say ESP MD5. And this is something that we will then put into an IPsec profile. I'm going to call it IPP, set my transform set, set 1, and also activate ID2 for the session, for negotiation. The way that we will activate ID2 is going to be by referring to the ID2 profile, this one. Set ID2 profile and its name. Right, so the next step, section IPsec and ID2. In the next step, you will have to define a tunnel for the VPN. We will say interface tunnel 12. I need to give it a subnet and an IP address. This is gonna make a VPN overlay. Just a network or just a subnet that identifies the tunnel itself. Let's go for 172.16.12.1/24. I'm gonna shut the tunnel down. The reason that I'm shutting the tunnel down is that with FlexVPN configuration, the interface tunnel will automatically try to negotiate the tunnel as it is up, and when the tunnel protection is applied to the interface. The tunnel protection is essentially the IPsec profile. So once you apply the profile to the tunnel, it will immediately try to start negotiating, which I don't really want to happen now. Okay, tunnel source is going to be my physical interface, and tunnel destination is going to be router 2, 192.0.2.2. Tunnel mode is IPsec IPv4. You could technically use GRE, or you can go for a regular IPsec with IP version 4, IP version 6. You even now have this overlay option that allows you to use a different overlay, a version of IP, just a different version of IP, I should say, deployed on an overlay than what you use for transport. You could do the opposite, like use IPv6 for transport and then v4 overlay. With GRE, you can use a single tunnel for both, for any combination. But in our case, it is going to be IP version 4 in IP version 4, like a regular SVTI config. So tunnel mode IPsec, IPv4, we've got the source, we've got the destination. We've got the address. One additional thing is going to be to say tunnel protection, IPsec profile, and this is how I activate our ID2 and IPsec related settings. Just point to the IPsec profile. Okay, the tunnel is once again shut down, so we will not see anything in the data plane right now. We still need those commands. We still need to configure the other device. And the configuration is going to be pretty much a mirror image. The easiest way to add those commands on R2 is going to be to copy this stuff to Notepad, modify the settings, and then paste to router 2, which is what I'm going to do. I'm going to say do show round section ID2 or IPsec or interface tunnel. I think this is going to cover all commands that we need for the peer. Okay, this goes to Notepad. And let's just go over those components one by one, trying to see if we can leave the settings or maybe if we have to modify them. So the proposal must match on the peer. The actual policy must match on the peer. So I'm going to leave this portion. We've got a key ring, which is, well, it points to a different arrows. This is just a description, but arrows must be definitely changed. We want to point to R1. Once again, this is the configuration for router 2. So I want to point to R1 as my peer. I want to keep the same key. I want to match connection coming from R1. So this is also, I need to also change this. Authentication is the same. Key ring, we've got it here, stays the same. Transform set, those functions must match between the peers, so we will leave this. The IPsec profile, I can leave it. Interface tunnel, same subnet, different IP address. Tunnel source still Giga1. Destination, I'm going to point to R1. Tunnel mode protection, this stays the same. Okay, I'm going to copy and paste to R2. Let's also say do show run section IGV2. So double check everything. We've got the proposal, we've got the policy, we've got our credential store, the profile matches connections from 1. Key-based authentication, local key ring, and then if we take a look at IPsec settings, we should see a transform set, we should see profile with IKE profile included, and then the interface configuration, just a different destination, and the IP address. Okay, so this looks good. Okay, with a configuration like that, as soon as I bring the tunnel up, it is going to immediately, the device is going to immediately try to negotiate the tunnel with the peer. And the reason for that is that this is an example of a so-called static virtual tunnel interface. So the syntax for FlexVPN and ID1 for the tunnel is actually the same. And the thing is that since this interface is static, it contains the destination. Destination is defined statically. The device immediately knows what's the peer, and it will try to bring up the tunnel when I know shut the tunnel. We don't need any type of access list with FlexVPNs. We don't need it for encryption because the device assumes that all communication that we will route to the tunnel is supposed to be encrypted. So it's like the traffic selector for the tunnel is set to anything. Okay, this configuration works well in our case since we know what our peers are. But if you plan to deploy this site-to-site FlexVPN tunnel, let's say on router 1, and this device would be configured with a sort of a broadband connection to the internet, like maybe cable, where the arrows will be assigned via DHCP. So in this case, you wouldn't actually know the address of R1 on the other peer ahead of time. And the way that we used to solve this with IPv1 was to use dynamic crypto maps. With FlexVPNs, crypto maps are no longer used. What you could potentially do instead would be to use a different type of a tunnel interface. It would be virtual template. Virtual template type tunnel is an equivalent of a dynamic crypto map in IPv1. And maybe let me quickly show you the difference in the configuration. I believe that one of the examples shown in the doc CD, we go to iOS 15. Let's say 15.6. Let's look at configuration guides, and then down to security, secure connectivity, and FlexVPNs. And let me open, I opened EasyVPN. I was thinking about FlexVPN and IPv2 Internet Key Exchange version 2, this one. I'm going to open up this configuring Internet Key Exchange v2 and FlexVPN side to side a link, and we will go down to the bottom, and then let's scroll up to the configuration examples. I believe that I saw a config example for this dynamic version of the tunnel, which I believe is this one. This is a branch, so the branch will generally know what the main office is. We assume that main office is a fixed address, but in that central location, we don't necessarily have to know what the branch addresses are. In this case, we would go for this template. We would only specify a tunnel source, but not tunnel destination. And we would also point to an unnumbered interface. This is all needed so that virtual template can get eventually cloned for each of the connecting device, taking a form of a virtual access port. Because remember, one of the, I would say, paradigms of FlexVPNs is that our tunnel interfaces are always supposed to be point to point. So even though we technically have just one virtual template, this is a source of parameters for other interfaces that will eventually handle the actual connection. So assuming that I have, let's say, 3 different peers connecting to the template, like 1, 2, and 3. If I negotiate tunnels with each of those peers, we would see 3 separate virtual access ports for peer 1, 2, and 3. And those virtual access interfaces will derive some of the configuration from the template and possibly some other parameters from the session, from the actual negotiation. So we will still have a separate interface for each of the peers. But in our case, this is not really needed. I don't have to use the template type tunnel because we know what the addresses are on both sides. So it is okay to use the static tunnels. Okay, let me quickly bring the tunnel up on router 1. Let's see what happens. Let's say no shut. You should see a message that is going to tell us that the ISACAP kicks in. This is now IPv2 based on the profile that we put on the tunnel. It says the tunnel comes up, but we are going to have a problem. In this case, we are going to have a problem in the data plane based on the fact that we've got a firewall between our VPN peers. It's a regular ASA, which is configured with the outside interface over here towards R1 and inside towards R2. As you probably guessed, this interface has a lower sec level than the trusted port, and based on that, I can tell that ASA is going to be dropping communication coming from R1, which it is. So in the data plane, we will have to add an entry for not only the negotiation, not only the control plane, but also for the data packets. I'm going to say access list outside the end permit UDP from this peer 1111 to 192.0.2.2 over port 500. And we will also have to add ESP, not for the negotiation itself, but for the data plane. If you know that there is going to be some sort of a translation between the peers, you would also add 4500. Okay, but in our case, it should be sufficient to add just these two entries. Okay, let's also bring the tunnel on R2, no shot. And let's wait for the devices to start talking to each other. Let's see if the negotiation is actually successful, or maybe I misconfigured some of the components. The way you can verify this is going to be with the show crypto IV2 session command, ideally with the detailed keyword. And the status you want to see here is supposed to be ready. Ready is an equivalent of a QM idle or main mode active on iOS/ASA. So this is showing me the addresses of the peers, local versus remote. It is showing me the policy for IKSA tunnel. So for the management connection, it tells me who initiated the session. It's R2 in this case. And it also shows me the identifiers of the peers, IKE version 2 IDs. This is pretty important because this is what your profile is looking for to find a match. We use IP addresses. This portion is related to IPsec, to the data tunnels. You can also take a look at it with show crypto session detail. But this command is going to show us the counters. Encryption and decryption. Let's also say show crypto session over here. Okay, but the problem we run into now is that if I were to ping from 3 to 4, we see that the tunnel is up. We've got the tunnel, we've got the tunnels in the data plane. The encryption domain is fine, but if I try to ping from 3 to 4, let's say I'm going to say show IPsec 10.24.24.4. So I'm trying to get through the tunnel in this direction from 3 to 4. This is not going to work because our VPN peers, they didn't exchange, they are not populated with the actual routes needed to route the communication for the tunnel. So I can try to ping to 10.24.24.4. We are getting the unreachable message from R1 because R1 doesn't have a route to the peer subnet. It says no route. Okay, and we have essentially 3 ways as how we can now fix it. Okay, our solution number 1 is going to be to use static routes. So this is the simplest option. Okay, another thing we could do is going to be to use dynamic routing. It is supported with FlexVPNs, but there is also what is known as IKV2 routing, which is basically a certain attribute, a set of attributes that can be negotiated between the peers during the negotiation. So if those attributes are meant to be used for routing, the feature is called IKV2 routing or FlexVPN routing. course, the easiest option, but also in the same time the least scalable, is going to be to add a route on both devices. So to get to 10.24.24.0/24, I want to go via the tunnel. And then on R2, I would say IP route, what's the subnet? It is going to be 10.14.14.0/24. I want to go via the tunnel. And with this in place, we should be able to ping across the VPN. If I say show crypto session detail, we see that we have connectivity. And this is all going via the tunnel. Okay, let's remove those routes. And let's take a look at the other method, dynamic routing. I'm going to say that we will enable EIGRP. Let's say process number 12. This is going to be AS12. And I want to enable the process on the VPN tunnel and also on the protected subnet. Now let's say show IP EIGRP interfaces to confirm this. So we've got the process running over here, Giga1, and we have it running on the tunnel itself. Let's say that this is going to be the tunnel. So over here as well. Now notice that I don't want to enable the routing on the underlay. I don't want to do this because I don't really want to start advertising the underlay to the peer, because underlay is what I used to build the tunnel. So in certain cases, you could run into a situation that your peer, after getting a route from you, might be potentially preferring the path, the underlay path via the tunnel, which would break connectivity. We only want to enable it on the tunnel, on the overlay, and on the protected subnet. And you will do the same thing here on R2. I'm going to say router EIGRP 12. Okay, let's go for the tunnel. And then the protected subnet 10.24.24. Do show IP route EIGRP. You see that the neighborship adjacency came up. We are getting the prefix via the tunnel. Do show IP route on 1. How do I get to the protected subnet? Via the tunnel. And I know this via EIGRP. So we should be able to ping once again, which we do. Okay, but this is not what I wanted to focus in this session. It's good to know, of course, how to deploy these two solutions, but there might be cases where static routing or dynamic routing is not going to work really well, especially if you think about one of the recent technologies coming up, like Internet of Things, devices with low power, or maybe on-demand circuits where you have to pay for how many bandwidth you use. You don't necessarily want to exchange keep alives in a form of dynamic routing packets over a link because of limited power or maybe the bandwidth restrictions. This would be an example of where you could deploy this third method, IPv2 routing, which is just a different approach to exchanging, certain session attributes over the during the negotiation. And this is exactly where this I said optional component is going to come into play. So AAA is what is going to be used to point to the attributes that we will want to use exchange within the session. And then configuration exchange, which is one of the IPv2 features, native features, is going to act as a transport for our attributes. And as we will see in just a moment, configuration exchange can be performed using two different sets of messages. We've got the request reply approach, and we've got the push model, which is based on set and acknowledgement messages. Now, the key thing to remember about these two options is that request response, this is only available on the, this is only triggered by the initiator of the tunnel. Versus the second model, set acknowledgement, the push model, it can be used by any of the devices. So this is what I want to focus on for the remaining portion of this session. Let's quickly remove the ERGRP process on both devices. We will lose the prefixes. And now in order to use the maybe not necessarily configuration exchange, because configuration exchange is by default enabled. Let's take a look at the showrun all section IGV2 profile. Okay, there are some hidden commands that are part of the profile, IGV2 profile, that you don't see in the configuration, and it is the config exchange request. This command is what enables configuration exchange using this request reply approach versus the configuration exchange set send, and possibly also accept if you want to use the attributes. This is how you perform configuration exchange using set and acknowledgement messages. And as you can see, these are by default enabled. They are configured in the profile. So this is now being used. The problem is that we didn't configure any attributes to exchange using this method. So if we were to take a look at the box, we would see that a peer is asking for attributes. We don't send anything back because we didn't enable anything. We didn't configure any attributes we want to share with the peer. So we will not have to change this. We will have to configure a database of attributes, and we will use AAA to point to those attributes. I have to build a single method list for authorization with AAA. When I say AAA authorization, we will perform authorization to the network. Let's call this a list AAAZ, or just AAA VPN. And I'm going to say that we will perform authorization locally with the locally defined policy. And we will now have to define this policy. So I will say crypto IGV2 question mark. What's the syntax? Authorization policy. I'm going to give it the name VPN POL. And we're going to focus on the IGE version 2 routing. So I want to use the route command. The route command is used to configure IGV2 routing attributes. Some other attributes that you can exchange, it includes information like the DHCP server, maybe DNS servers, the pool, some lifetime, and some other options. But for IGV2 routing, it is going to be the route command what you will have to use. And in this policy, I'm going to say that I want to push, what I want to push to the peer is going to be a subnet configured on my protected interface, which is Giga1. So what we should see, so what this command does, it says that I want to push a route that is configured or is associated with my Giga1, which is going to be this subnet on R1. Okay, for this policy to be activated, we have to integrate this configuration with our FlexVPN. I'm going to say showdown section ID to profile. We will have to go to the profile and say that for AAA, we want to do authorization for the group. In this case, a group or a user would work. The key thing is that we have to point to we have to tell it what authentication we use. What's the authentication method used for the session? It is the keys. So I'm going to say pre-shared keys. And then this is my method list that I call AAA VPN. And the method list says use local database. So when I put this here, the device immediately knows that it should be looking for the policy locally in the running configuration. And this section, the AAA username, is basically the policy name. So what's the policy name? I called it VPN POL. Let's look at the profile once again. So this is how you do the integration with AAA. In our case, it is only authorization. It says use local database. This is the name of the policy defined in the running configuration. I need to, let's just say showdown section policy. The policy is here. It says this is the protected sum that they want to send to the peer. Okay, and we will do the same thing here on R2. I'm gonna copy the, let's say, showdown section policy or AAA. I'm gonna copy this, paste over here, and we will then copy the policy. Policy definition of our attributes, and we will then activate this policy. So go back to the profile and put it over here. It's same syntax. Okay, and maybe let's shut the tunnel on R2. We should see that the SA is going to be cleared. And I'm going to enable the box. So router is going to act as the initiator of the tunnel. This is what I wanted to show you here. The 2 is going to act as the initiator in this case. Router 1 is going to act as a responder for the session. So we will send our packets from first packet, I can say, and a request is going to be sent by R2. It is going to be sent to R1. I'm going to keep the tunnel up on R1. I will just say log to the console at level 6, log to the buffer at level 7. Let's clear, let's say logging enabled, logging on, and do show logging just to take a look at this config. Okay, console says 6, buffer says debugging, and the buffer size is, it should be enough. I'm gonna say clear the buffer, yes. Do debug crypto ID2, and we will then no shut the tunnel on R2. So I want to show you the debug messages. We will take a look at the negotiation. Do show logging. So let me quickly tell you, let's go over those messages one by one and see what's exchanged and when. And the reason that I'm showing you this now is that I also want to point to a difference in the configuration exchange after slightly modifying our config on the peer. You just scroll to the bottom. We see a lot of messages. Maybe let's just verify if the tunnel is actually up. Let's say do show crypto session detail. It says the tunnel is active. Do show crypto session, to show crypto IB2 session detail. Okay, the status is ready. We see we got a remote subnet from the peer. When they say show IP route static, those routes are injected as static routes. Okay, in this case, this route is not injected. If we take a look at R2, do show crypto IB2 session detail. It says it got the prefix, it got the attribute, but if we take a look at the routing table, okay, so it looks that to inject the prefix, let's make it clear, show IP route static. The route is on 2, but is not on 1. The show round section IB2. Let's take a look at the policy once again. Okay, so the policy is defined over here. Do show round include AAA. We will have to double check the settings here because I would expect or want to inject the route as well. This is the method list. It is local, so we point to the policy over here. The policy is referring to Giga1, which is fine. So this will be sent to the peer. And then the profile, AAA authorization group, key-based authentication list is this, and the policy name is VPN POL. Okay, this is fine. We may actually need to shut down the tunnel and bring it up again. But before we do this, let me also check the do show run. Let's just say show crypto IB2 authorization policy. I want to see if we have the route accept command in place. We have it. So we have to bounce the tunnel. This is we'll have to reinitiate the connection once again. I'm gonna say interface tunnel 12. I'll shut it on 1. Interface 12, shut it on 2. Okay, then bring it on 1. Clear the log, clear the buffer. And then no shut on 2. Let's take a look at this. Show IP route static. Okay, so now we see that it injected the prefix. The question is now who was the initiator of the connection? It says, okay, it says initiator of the SA no, which means that R2 was initiating the session, which is fine. And let's now take a look at the buffer. Okay, so we should see that the first message it got was a message coming from 2, which it is. It says this is the INE exchange request. So, okay, so this message, this first negotiation, is all about exchanging the cryptographic functions and the Diffie-Hellman information. So in a reply to this, we should see that we will send our own packet. So we send packet to the peer from us, and this is INE response. We've got the Diffie-Hellman payload, we've got the cryptographic functions. This is what we send to the peer along with net detection. The payloads, this is not needed in our case because there is no net, but it does that by default. Okay, phase 1, old style phase 1, or just INE exchange is now done. At this point, we know that we have that INE up and running. So I got another message from the peer, which is the INE authentication request, which includes the configuration payload. So as we will see, since R2 is acting as the initiator and configuration exchange is enabled, this device is trying to request an attribute or just attributes from the peer from R1. So after authentication takes place and it is successful, we should see that the device will try to get to the, well, since we enabled AAA on R1, we enabled authorization. It does that authorization lookup trying to get the attributes. It got the attributes, which is our subnet. Now in that, so it kind of like buffers those attributes for the session. Now the other portion of that request, of that INE authentication request, was the config request exchange payload, where the device is looking for additional attributes for the sessions. So just to make it clear, those attributes that we will then eventually push or just reply, send back to the requester, this is what we got during the authorization, which is from the local database. And at some point, as we will see, we will reply to this request with a config reply message, which is going to include our protected subnet. So this information, because this is the only attribute that I configured within the local policy. Okay, so let's look at this. It says I'm building configuration reply with our local subnet. And this is what we will include in the INE authentication response. The response also contains configuration payload. This is config reply. This portion, plus the iOS version. Now, if we take a look at the other portion of the exchange, we will also notice that following the INE authentication, PC authentication was successful. This covers INE authentication. Following authentication, there is also that optional informational exchange where the peer is pushing as its own attributes, the 1024 subnet, so we can use it on our end. Now, since 2 is the initiator, it couldn't use the request response option because this one is only for initiators. That's the reason why it was the set message what was used to push the attributes with the acknowledgement sent by us by router 1 accepting the received information. So this is how we exchange this data. And maybe one more thing we will do at this point. This is actually the last thing I wanted to show you in this session. I'm going to say show run section INE profile. We will disable the request response exchange and see what is going to be the end result of this configuration. I'm going to say config exchange request. I want to disable it on R2, and R2 is still going to act as the initiator. So when I shut the tunnel, okay, R1 knows that the tunnel is down, and we will clear the buffer, show the bug. The bug is in place, and you will now shut the tunnel. Okay, what we should see here is that we will still have that prefix injected, but the information this time was not obtained using the request reply message. It was obtained with the, actually I'm showing you the wrong device. I was supposed to show you the this routing table. So this prefix this time is not obtained via the request reply message, but via the configuration push with the set/acknowledgement. Let's go ahead and take a look at this in the logs. So the beginning of the negotiation is going to be the same. It says I got a packet from 2. We are on router 1. I got a packet from 2. We are negotiating keys with the Hellman. I'm replying with the selected proposal, the Hellman key materials. We've got the SA up and running. So the peer, the initiator, R2 sends the starts authentication exchange. Notice that we don't get any config request message at this point. We still do the authorization after authentication because this is what we configured on this unit, but we didn't get any config request. We disabled this with the no config exchange request on the peer. Okay, since there is no request being received on router 1, there is no need to send any response. So we immediately cut down on those 2 messages with the single command enabled on R2. But we still got the prefix, we still got the attribute through the set acknowledgement exchange. So it said I'm replying to router 2, we finish authentication, but in the same time I am pushing the subnet. It's unsolicited message. Peer didn't ask me for that, but I'm pushing this information because I've got the attributes configured and I am supposed to use the set configuration exchange. So I'm pushing this information to the peer, and the peer accepts this information and also sends me its own subnet. So we got config set from the peer with 1024. So just to recap the request response, this is something that you can only use on the initiator versus a set acknowledgement. You can use those messages on both devices. Do you guys have any questions to this session, to this demonstration? Let me take a look at question section. Okay, I'm gonna wait for the next, like, let's say next minute. If you have any questions, just go ahead and let me know. There's just one question I see. Provide the configuration file for future reference. Well, this is something I can definitely send you in an email. So I'm gonna do this after we finish this session, which is actually happening now. I wanna thank you guys for joining. I hope you find this information valuable. Thank you for attending, and I'll see you in about a month in a different webinar. Thank you.